Welcome to this session on planning. So let's hallucinate together a bit. I was thinking that and that's just a personal observation, in the age of agentic AI, we tend to dive straight into implementation. Connect an LLM, add some tools, resources, and let the system figure it out. Not very architectural, if I can use this term. I'm Dan Dobrin, I'm an app architect in Google Cloud. I focus on application, Gen AI code-assisted tools. It's a distinct pleasure to join Spring.io as a speaker this year again. I was thinking that when I was planning this talk, that we would talk about determinism in agent and a number of planning patterns, kind of like plan on how to plan our agent. However, as I was looking into what is the actual elephant in the room, a number of different things actually come to mind. So sure, okay. That's the elephant in the room, unpredictable passes. So same input, different execution paths every run. Untestable behavior, traditional unit tests simply don't apply to agents. There is a hidden cost multiplier, so token usage without guardrails could compound quite fast. Now, if we are looking at debugging, which we were accustomed to, there's no stack trace in terms of like, why did an agent actually decide this? There's this infinite loop risk of agents chasing their own tail if there's no exit condition. But one thing which stuck to mind was this idea of model variability. The same prompt generates widely different answers. The second thought came to mind as I was exploring this is in terms of observability. In the past, we were used with a deterministic approach. Code was the source of truth, and we were measuring CPU utilization, memory limits, whatnot, network latency. But in the agent observability, behavior is non-deterministic, and the reasoning is the source of truth. So many things become interesting for us to capture. Tool call sequence, the reasoning path, how did an agent get to this particular conclusion? The decision quality, the time to the first token, user experience could be affected if that is not appropriate. And token consumption, it's not just an issue of cost, but also the idea of token efficiency. How many tokens do we spend to get a quality response? I built this little application, which we will be running now. I hope you can see that. So the same system prompt in an application, the same user prompt. I want a brief answer to this question. Spring.io is the de facto premier conference for Spring in Europe. So as different models, and I configured two of the Gemini cousins and a model from Claude. Each one gives us different answers. Gemini Flashlight as well. To evaluate this, here's the verdict. Haiku says, well, requires context. Gemini Flash says, well, Spring.io is widely considered a de facto conference. If we aggregate all these responses, the answer becomes like, here is the case for yes, and here's what we decide. So we see all this model variability. Let's run this again while we look into this pattern. We'll run this again in a different way. So I think this agenda had to change a little bit. We have to add observability, and we have to introduce the multi-model deliberation as a new pattern, not the original patterns I had in mind. Let's add this LLM council, and in the end, understand also what consensus metrics would come about. So this pattern came out from an archive paper. Then Andrej Karpathy of Tesla and OpenAI fame vibe-coded an exercise. And the idea is that no single model is always right. A council of models is more reliable than any one genius. The problem is that single LLMs hallucinate with confidence, like with no built-in checks or balances. The council takes a number of specialized agents, deliberate, challenge, and synthesize the answers with an outcome of a higher accuracy, explainable reasoning, and reduce single point of failure. Now, why would we do that? What do we know which model is best for our query? So the problem is that no single model wins across all tasks. And without structured evaluation, you're kind of like guessing. The architecture inside, as we build this, we want to separate the generation of a response from the evaluation and have clear optionality across generator and reviewer tool. Conceptually, imagine a room of experts, each from a different school of thought. Let's say all of us here, we're given the same question independently. Each one answers anonymized, then each one ranks and critiques the others without knowing who it is. And in the end, the chairman synthesizes the collective wisdom into one answer. That was the original idea posted in that paper and discussed by Andrei Karpathy. I've added a number of things to show that actually there's even more variability here. The chairman could be one of the advisors ranking it or not. Why? Because LLMs generally tend to be harsher on evaluating their own responses rather than somebody else's, even if anonymous. So the architecture of this application, we start from an application that is production ready, from coding standards to retries to all the features which we are accustomed to, but we're not saying this is the most efficient thing. This has to solve a problem, and we're going to evolve this as we go along. So we want to have a 5-stage deliberation process, which we ran now. In the meantime, it collects individual responses. It will do a peer review ranking. So each one ranks it anonymously, notice like different letters so that they don't know about each other. Each one provides a ranking. There are separate non-LLM actions, call them tools if you like, for aggregating the rankings, pure math, an agreement analysis, disagreement analysis, capturing some metrics, and the final consensus. So we can have these 5 steps which we would like to use. But we want to see also traces for this particular application. As we look at traces, this becomes now important for us to see which model, how much, what the latency was, and take all these numbers as, this is just, we look at them comparatively, don't take them as absolute numbers. If we run it again, it's going to be a different value. And if we are looking at these numbers, we want to observe them also in a tracing. I am using here Google Cloud Trace. It is available to me, and we can see the correlation, and we can see different information about each of the agents. So if we look at the last one we ran, it involves all the steps. We can see each one, and we can see the agent reasoning, which one was called, how each one runs, what data we collect. And we want to collect things like, for example, like the token prompt, the time to the first response, different information, as well as aggregate information. Were there any errors or not in our application? The app is built with Java 25, Spring Boot 4, Spring AI, the latest 2.0 milestone 4, and uses a Vaadin Hila 25, the latest versions of each one available to us. You can run it as well deployed in Cloud Run as a serverless environment, and it scales up. Now, what design principles did we apply here? One is anonymity. Models evaluate content on merit alone. Collective intelligence, because if we calculate agreements will surface high confidence insights, and disagreements will point areas of genuine uncertainty. Then structured deliberation, because we have a fixed multi-stage pipeline, which ensures that every perspective is heard. And provider independence. All LLM providers are interchangeable members. I picked here lightweight models like Flash and Flashlight, but you can just substitute them the architecture. The deliberation process doesn't change if we use Gemini Pro or Claude Opus or whatever other model we would like to do. By running them in Vertex, I can pick any model I want from Hugging Face and just plug it in. So what use cases do we have here? Well, one is I'm not suggesting that you should run it for every single model call, because you run multiple models. Therefore, it's good for model evaluation, for testing, to seeing which path applies to your particular use case. It's good for creative brainstorming at scale, for fact verification and cross-checking across each models, complex multi-factor decisions. And if we were to apply this in any one industry, investment and financial research, where you want multiple analysis would be one area to focus on. Now, we know the advantages, but what are the trade-offs? Of course, there could be multiplied API cost and, of course, latency. Parser fragility. Not all models support structured responses. Sure, the large models do, not all of them do that. This first implementation has a volatile session state. The state is in memory. Instance fails, we lose that. The chairman is a single point of decision. So, of course, you should always try different models as the chairman. And we can improve the performance of this particular application. Now, what is our next step? Let's use this pattern and apply this for all the other patterns I had initially in mind. So we have an entire spectrum from strict compliance as a workflow, deterministic graph, very clear. Strict execution, one step leads into the other. At the other end, we have the Supervisor LLM, where an LLM orchestrates the delegation of different sub-agents. And we can impose some constraints, so that's why we call it bounded flexibility. In the middle, I firmly believe that the truth is always, there's never like a black and white. There's a hybrid approach, and the combination of multiple approaches will be the winner in the long run. The goal-oriented action planning approach, which was first released a year ago in Embabel, is now available together with workflows and Supervisor LLM in Google ADK. I have added these planners last Friday, so this is the first view. You can see them. You can see them in action. And as we explore these three, there are also other patterns which are closer to, let's say, each one of the edges. Like a hierarchical task network is a workflow which needs one LLM call and execute the actions. On the other side, utility AI, which comes from the gaming world, same as the goal-oriented action planner, is used for explorations where we don't necessarily have a goal in mind. So let's look through them and look at the two ends of the spectrum. So deterministic, a compile time graph, zero planning calls, predictable, reproducible, preset compositions. If we take an image, we have to analyze it, enhance the image, store it. That's a clear workflow usage. On the other hand, non-deterministic, where we need runtime LLM planning. If we have, in our case, either 3 actions or 5, or 2 just for a quick consensus, we need an LLM call in between. But we can, on the other hand, interact with it with natural language. Instead of having predefined here, I click a button, we can say, have a full deliberation or get a quick consensus, which is more natural to us. And it allows us to use adaptive partial workflow. So ADK workflow on one side, ADK Supervisor LLM on the other side, with a number of others in between. We're going to explore them one by one, jump from one to the other, and leave the goal-oriented action planner for the end. So the workflow pattern, compile time graph, It's the same, if we think about it, the same application as the first one, but now you're having a reusable agent. So we're introducing agents which we will use unchanged across all the patterns. The way what changes is the way we orchestrate them and the way we plan for them. So a layered approach. What can we change here? It has sequential parallel steps. So one thing we see, once we have the individual response, we can review, but we can also get agreement and disagreement. They all need the individual response. So one good thing would be, let's parallelize these requests. Now, the advantages are zero overhead, deterministic, lower cost. If we think about it, that we know we can quantify the cost. That could lead also to higher cost. The shared agent code base all the way across all our different planners. And we know that from the beginning. The trade-offs, takes presets. No natural language control, no partial workflows, rigid parallelism, which we impose. So potentially also higher cost. If we want a quick consensus, why should we run, for example, all 5 of them? That might lead to a different cost. So how about we run this now in, we run a workflow. I'm going to run them not in Cloud Run. I'm going to run them in on the machine just so that I can show you some of the logs and some of the adaptive replanning, which we will see in later models. Patterns. Can you see these logs? All right. So if I'm going to run here the same question which I ran before, and I'm going to say run this deep analysis, I expect this to take less time than the previous one because I'm going to parallelize these operations. So I can see them, I can see evaluation of responses, and for each one we can measure the model, the latency, as well as the token count, and we can see how it would execute one of our operations. Oh, very nice. I was running the wrong, absolutely. No wonder. You'd have too many. Let's allow this to start. You can see this, you can see it start up. All right, this seems like a little different. So let's allow this to run. Now, workflows very clear. But you saw this application started, the Spring app, it started in probably like 6, 7, 8 seconds. Is there another problem when we think about agents? Startup and startup performance, which was important to us, and throughput in services before, especially in serverless environments or environments with high variability in scaling, is important to us as well. And we can run a native image with GraalVM, which will start in a few hundred milliseconds, so we can put the rest, the scalability issues. If we move into the Gen AI world, it does not mean that we should be changing the approaches which we have. So this ran, and now we can see in the traces, we can see that this entire flow now ran in 29 seconds. Why did it do that? Is because if I'm looking at the trace log, I'm expecting to see these operations in parallel. So it is a controlled parallelism which we have available here. So we can see them all running in parallel. All right. So this would be fine for us. Now, let's explore the other end of the spectrum. Bring this back and start our other application. we can run this. So at the other end of the spectrum, we have the Supervisor LLM. So the Supervisor LLM is like LLM-driven iterative planning. It has a core loop structure and some design invariants. So you observe, you build a context from the current state, you look at the agent catalog, all the agents which are available to you, then an LLM will select the agent to execute, and of course, at the end, it's responsible for emitting a done signal so that the loop finishes. It executes the agents, but it can decide to run some concurrently or some not. Updates the state and continues the loop. There are some design invariants like stateless planning. Each time after each agent call, it has to reread the state and build its context. It's probabilistic dispatch. There's no workflow here. We do not know exactly which step it would call. There is an emergent parallelism, but it's not in our control. It's in the model's control. And there's a bound determination. So we need to impose some rules in order for this not to be a runaway train. One would be workflow rules, to know what our intent is. And we need to know what, if we have a goal, what is it that we're trying to achieve. The second thing would be chain-relaxed structure. We use domain objects throughout the application, and we need to know that a particular domain object matches the output matches the input of another one. And there are also workflow filters. We want to know that no additional agents, which somehow can creep into an agent catalog, are used outside of what we are planning to use for this particular run. What are the advantages here? Natural language control. We have dynamic parallelism. We have three-layer safety nets. Otherwise, it would be like the simple agents we built like a year ago. Last year, I had an agent. Here's a prompt, a number of tools, and sometimes it would call it 3 times, 5 times, 7 times. I've seen it even 9 for the same goal. Now, the same agent code base throughout. But there are trade-offs. Each step, it will call an LLM to make the next decision. It's non-deterministic. It might choose different execution passes in between runs. The same parsing fragility remains. We have to introduce a maximum iteration cap because we don't want this to run forever. And we will have keyboard-based workflows. We have to introduce some in order to get the LLM to follow specific passes. So let's run now. The supervisor. I am not Josh Long or Anton, so I don't automate or type as fast. So I'm just going to copy and paste some of these prompts. So if I'm going to say get a quick consensus on whether Zinger is the gold standard in Porsche restoration as a company. I'm a big racing fan, so there are these companies. If a Porsche is not expensive enough, you can take one, and there are different companies adding whatever crazy things to it. But we want to know, is this the best one? If I ever decide to have one, then which company should I go and use for that? So I'm expecting that it would not call the entire, it will not call the entire set of actions available to it. So it did. It looks only at the agreement. I'm asking which one. Is this the best one? And the final synthesis says that, yes, Zinger vehicle design is the gold standard of modern Porsche restoration. But if I'm changing this to deliberate on Zinger, I'm inviting a discussion. So deliberation, I'm inviting an agreement, I'm inviting a disagreement in here, and I'm expecting to see that all stages are used. Now, of course, we can have a much more complicated application, but this is a use case which I think we can all easily understand. So we can see the individual responses for each one of them, and you can see all kind of different opinions. It collects the rankings. Each one has peer rankings. We run agreement analysis, disagreement, and in the end, what do we see? We see ranking consensus and disagreement. So I added an additional consensus metric. Even these could be varied, and it depends what are we using. Ranking consensus and factual agreement, they both think to be on the agreement side. They're actually orthogonal. So we always need to think when we plan, not just pick the right plan or planning algorithm, but also pick the right non-LLM operations, because those could introduce variability for us as well. Now, moving on from supervisor, let's bring us back towards the planning, the workflow part. So hierarchical task network is this idea of a top-down decomposition with a greedy method selection. We take a task, we have a world state, we know the agents which are available to us, and we take a method, let's call it a method, it could be any kind of method or a function, which will look at compound tasks, it will prioritize them, and it will decompose them into subtasks, recurse on that. And in the end, it will end up with primitive tasks which have preconditions which get added to the plan and executed. For example, if I start with a goal, I know that I have to start with individual reviews. The output is an individual response object. That is an input for several others. And depends on what I'm going to achieve, I'm going to follow different passes. Now, the difference to the workflow is we know the agents, we know preconditions, post-conditions, but we need an LLM call to help us make a decision, kind of like which path, do a classification, which path we're going to follow. The architecture is based on a query classifier, which will use 6 categories which we have predefined. They are like factual, opinions, or analytical, or creative, or it's a debate, or informational. This is something which we will apply as SMEs in our particular use case. And then there's an execution of the plan, which will dispatch every single task, and everything runs with reactive streams. Now, what are the pros and cons for this? We have adaptive pipeline, so we can add additional steps, pure additional extensibility. There's no architecture change, there's no change in the debate model. We know upfront, by using sealed interfaces, we know which agents could be run. We have a graceful degradation. If the LLM cannot match either one of the categories, we assign a default and we assign analytical so that it runs the full exhaustive set. There's no orchestration of the LLM calls. Now, the trade-offs are that there's no backtracking. So once the choice is made, that's what we execute. There's only a sequential execution only because we decompose the task, and this is how everything was added. There's a classification dependency. It very much depends on the classifier accuracy. Did the model pick the right classification or not? Of course, there's a fixed method set, and while each classifier returns a confidence score, well, methods don't use them because once we set this up, it is as is. We cannot reuse that. So let's see this in action now. Let's shut our system down, and to just alleviate the discussion on startup speed, I started the application, and it started in 400 milliseconds. Now, of course, each time you run, and this machine runs a bunch of things. If you run it in a Cloud Run environment, it might be 500 milliseconds, might be 400 milliseconds. I'm sure if I run it Again, this could be maybe, you see, 167. So rest assured, performance is not a problem. We're in the Java world. We're not in the Python world, where you might have some slight delays. So let's run now a hierarchical, the H10 algorithm. I have built H10 in utility as plain, purely based on the original app, just so that you can see that you don't always want to use an agentic framework. You might want to implement it, or you might come up with your own and implement it on top of an existing application. Don't take this as best practices. Take this as a learning set of tools from which we draw inspiration in how we build our applications and what patterns we apply. Now, if I'm looking at H10, I'm going to say list all Tom Cruise movies. Like, I don't know them. I'm not actually inviting a debate here. So the execution plan, it classified this as factual. What does it want? The individual responses. It wants to see the ranking, because some might be considered accurate or not. And in the end, a final synthesis. So the LLM took that goal, classified it, picked one of the categories, which is factual, and it will build our response. And we're going to see, if you're a fan of Tom Cruise movies, probably you would recognize them all here. Now, it could pick a different one. What if I'm going to select what is the best programming language for GenAI applications? So we'll see. This is an opinion. So because it's an opinion, it classifies it as an opinion. It picks the agents which are classified there, and we're going to see what it does. So let's see what we understand from that. So the point I'm trying to make is always look at what problem are you trying to resolve. That, I hope, comes pervasive through the different approaches. Think what applies to you. Sure, take it on a larger project which you're working on, your pet project, something you use professionally, and think what would apply here. So if we see flashlight says, well, Python says that undisputed leader is Python. Okay, I'm skipping Flash from now on. Claude. Really? Okay, so we're not asking this question again. So it tries to explain to you why this and that, and here's performance, and so on and so forth. But I don't know. I don't even want to know the final response, because I can see that probably the training data just has seen too much Python. So we have to skip. Skip on that. I'm sure it's going to be there, but I don't want to be depressed. So let's look at utility AI pattern. So utility AI comes from this, I'm not sure what the pronunciation is, this OODA loop. So you observe, you filter eligible actions from a world state, score each eligible action, decide on selecting actions select actions where the scoring is larger than a particular threshold, and then execute the selected actions in parallel. So we start from a world state, we filter the eligible actions. Each one has a cost. Some could be LLM agents, some could be just tools. We score and select, execute in parallel where we can, and update the world state. Well, this is great for exploration. This is great for exploration because we might not have a precise goal. We might just say, find me the best MacBook for programming, or find me the best laptop for programming. I don't really know what this could be. Lightweight decisions, because the scores are non-LLM based, implicit dependencies, we have adaptive strategies, and of course, full observability. Now, the trade-offs are how do we set up the right weights? And that is an exercise which we have to do via tuning and evaluation. The action set is fixed. It would explore only what it can see. There's a threshold sensitivity, and there's no backtracking. It is greedy. It's optimistic, and greedy tries to find what is the next best thing to get the best results. It's like my children. We're always going for the largest piece of chocolate in the house. So, and then you can, the state is pretty binary. It's available or it is not available. Did it actually say, oh, of course, it's Python, okay. So let's, from now on, that's it. Please do not use this. This is not a correct answer. So let's run utility. In utility, we want to see to make decisions on the fly, and we're going to run utility, and now we can pick different scoring strategies. A balanced one, latency optimized, information gain. We can assign different weights. So if we want, I would assume probably information gain is what we want to see here. And now we want to see how utility decides. So here's the exploration. It says it's a factual, verifiable list of filmography does not involve subjective judgment or debate. So it plans the item, and we can see this. I don't know, I hope you can see this. It runs the initial query, it gets the responses, it labels them, it anonymizes them. We can see what is complete and what is running. So now it makes its decisions. Collect the responses, yes, we expected that. And in the end, it will decide to do an exploration synthesis. This is what the algorithm with this particular set warrants. So we ran only 2. Did we get our list? Yes, we did. But how about if we were to invite a debate? Let's try now a balanced, which company does the best Porsche restorations? I can't let go of these cars. So by running it, it will tell us that it wants a full deliberation because best is subjective, depends on individual preferences for original versus modified specification. And with the confidence of 100%, it decides what it is going to run. Now we can see it running. What we also see is that utility will go step by step. By going step by step, it takes each iteration, it goes to the next one, and we can see the decision happening. It did rankings, now aggregate rankings, now we expect synthesis can run, but we expect agreements and consensus to be executed here. One after the other, they would run, and we could observe each of these behaviors. In the end, we can see the full response, and with a ranking consensus of 100 and a serious set of disagreement. Disagreement also means how they disagree amongst each other, not necessarily if that is factual. So if we have utility, we went on both sides from the extreme, we narrowed down to the hybrid. So in goal-oriented action planner, we start from a node, current world state, and we want to end up with a goal node, where it's a state which satisfies all the goal conditions. The edges are actions, if of course the preconditions are met. And we always want to expand the cheapest first. So we assign scores. Let's say an LLM operation has a score of 10, a non-LLM maybe 1. And we accumulate the cost so far with what we estimate the next step would be. And in the end, we get here the guaranteed optimal plan. It uses an algorithm, GOAP came from the gaming world, called a search, which will find a cost optimal sequence from an initial state and continuously updating the world state as it gets to the end. What is the important thing to know here is that after each step, you can replan. It's not that backtracking is not available anymore. Here, you can replan after step if conditions are met, and these conditions are in your control. Now, the advantages is that there's 0 LLM planning cost. This is fully deterministic for the same prompt. It auto-discovers parallelism. It's a cost-optimal path. Sure, we have the flexibility. Now, of course, trade-offs could be like the keyword-based goal selection. There's a fixed set of actions, sure. There's a limited runtime adaptation, and that depends on how we configure the scoring metrics. And there's the start search overhead. Well, it is, but it very much depends on how many you run, and it has no learning or feedback loop. So let's run this. Let's run this. This gives us what I am interested in, and I'm hoping the models do not disappoint me. I'm hoping now to force an adaptive replanning so that we can see that this behavior could change. So to take one where we can, force replanning, let's take the Go planner and say, run this full deliberation on this question. For a startup with 5 developers building a new SaaS product from scratch, which technology stack should they use? Ruby on Rails, Go with HTMX, Elixir with Phoenix, and which single option is the best overall choice considering hiring, time to market, scalability, and long-term maintenance? So the plan is set out. Collect the responses, run ranking, disagreement, and agreement analysis tells me they run in parallel, and then all the others, aggregate rankings, aggregate disagreements, and agreements. So the GOAP planner will intervene here 3 times. So the first time, this is what I want to see. When it reaches the 3rd step, it says, I've reached a consensus of 1, and in my conditions, I've set a threshold of 0.7. So because there is a high consensus, it skips aggregate disagreements. So it updates the plan and has only 1 single step remaining. This is important from us, and if we scroll down, I'm expecting disagreement. We see aggregate rankings, analysis. Here is the aggregate agreement. We see the disagreement, but we don't see the disagreement analysis. And we see now these ranking consensus and factual agreement. So it is balanced, and it allows us to also replan dynamically. But we talked about all these. Different LLM actions. So let's think about what consensus metrics we have. One would be for ranking consensus. Do the council members agree on which response is best? This is called Kendall-Tau. It's a mathematical formula. I looked up what mathematical or statistical method we could use. So what does it catch? Subjective, quality, convergence, split opinion. So that's great. What it misses is factual correctness. So it talks about agreements among themselves, not whether this is a fact or not. It's factually correct or not. So perfect agreement could go from 1 and then to a random contradictory to 0. We want to be, for example, we hope to be in a strong or perfect agreement if possible. Now there's factual agreement. This is orthogonal to the previous one, because here we want to see, do all the responses agree on the same factual content? So this catches content level agreement. Do the models say the same things are true? But it misses the correctness of the agreed fact. So again, there is a scale. And each one of these consistency metrics we pick, it depends on us. We have to test, we have to evaluate. There's no hard and fast rules. Always think that we have to find the best thing for our use case. So disagreement severity is a set of weighted factors like stance diversity, the balance of positions, and mention frequency in a particular discussion. Now, of course, we use quite simple prompts, and you see how much it generates. It's a lot more interesting if we were to run this run a code review over some larger code base, but we don't have time for that in a session. So this catches structure and intensity if there is a disagreement, but it misses factual errors or stylistic disagreements are treated in the same way. I want to leave you with this. Models will keep changing. New patterns will keep emerging. The best thing we can do is stay architectural, like coin a new term, and apply the right pattern for the problem in front of us, not the one that's trending. And remember that the best pattern might be the one you build next. Thank you.